So now let us apply what we have studied in a sample problem. So this is the sample problem. A pre-tensioned simply supported 10 LDT 24 double T beam without tapping has a span of 19.51 meters or 64 feet, and the geometry shown in the figure, although later I will show some details of the figure or the geometry of the figure, but as of now, you can just refer on this photo. So this is the simply supported pretension 10 LDT 24 double T beam. So you can see here that there is an image of double T, two T's. That's why it's called double T beam without any tapping, and has a span of 19.51 meters or 64 feet. So the geometry of the section will be shown later. Uh, if you will look on the tendon profile of this particular pretension simply supported 10 LDT 24, actually it has a profile that looks like this. So this type of tendon profile or pre-stressing reinforcement profile is actually what we call a harp tendon or harping, which is usually used for pretensioning. So this type of tendon profile is usually used for pretensioning. And in the case of post-tensioning, we usually use a tendon profile that is what we call parabolic. So it has a shape of a parabola. That's why it's called parabolic. So that is actually what we call drape tendon or draping. So this is the concrete element we are talking about, the pretension double T beam, although it is in the side view here. So if you will look in this view, it will look something like this. And it is a simply supported concrete beam according to the table, according to the problem, simply supported double T beam. And it has a neutral axis somewhere here with an eccentricity on the midspan. Let us just call its eccentricity all throughout the length as eccentricity E. Although if we want to find the particular eccentricity at say for example at midspan, it is equal to 375 mm or 14.77 inch. And for the end location, the eccentricity at the ends of the concrete beam is equal to 197 mm or 7.77 inches. So actually, these things are given on the question. So in addition to the superimposed dead loads, of course, and live loads that the retention beam carries, it is also given that the self weight of the concrete beam, the double T beam we are talking about here, has a magnitude of 5.24 kilonewton per meter or 359 pounds per linear foot. So that is the weight of the concrete T-beam uh, that it supports. So in addition to that, as given on the question, it is subjected to a uniform superimposed gravity dead load intensity WSDL and a live load intensity at WLL summing to 6.13 kilonewton per meter or 420 pounds per linear foot. So the sum of the superimposed dead load and live load is equal to 6.13 kilonewton per meter according to the question. So in addition to the self-weight, 5.24 kilonewton per meter, the concrete T-beam also carries 6.13 kilonewton per meter, which is the sum of the superposed dead load and live load that it will carry on the service load condition. So in addition to that information, the question also said that the initial pre-stress before losses is approximately equal to 70% of the ultimate strength of the pre-stressing reinforcement, FPU. So that is the magnitude of the pre-stress before losses. So usually, uh, that initial pre-stress occurs at transfer when the pre-stressing reinforcement is cut after it is jacked. So if you can remember the jacking operations that we have discussed on the previous meetings, after the pre-stressing reinforcement is jacked, after some time, after the concrete element already attained enough strength to resist the compressive force that will impose by the pre-stressing reinforcement, so that the pre-stressing reinforcement at that time will be cut, thereby uh, uh, exerting a compressive force to the concrete element due to the fact that it tries to go back to its original length, because we all know that the the pre-stressing reinforcement at this particular circumstances is already elongated. So the natural behavior of the pre-stressing reinforcement is to return to its original length. So it will try to return to its original length, but the concrete itself prevents it from doing so, thereby applying a what we call compressive force to uh, the concrete element. The stress that that compressive force produces is actually what we call the initial pre-stress before losses or at transfer. And then after some time, after the pre-stressing force is transferred to the concrete, after some time, the pre-stress force will diminish, as we discussed on the previous meetings. It will diminish. It will have a reduced value, and the reduced value is what we call the effective pre-stress after losses, after the pre-stress losses occur. And according to the question, the effective pre-stress after losses is equal to 1034 megapascal or 150,000 psi. So the question, the required value being asked by the question is the extreme fiber stresses at the midspan, which is here, the extreme fiber stresses at this particular section on the simply supported beam. So we want to find the stresses on the top and bottom fiber at midspan on this particular simply supported beam. Due to letter A, initial full pre-stress and no external gravity load. So what is the uh, stress that being experienced by the concrete at top and bottom fiber due to the initial pre-stress and uh, the self-weight alone, because it is said that there is no external gravity load. So when we say external gravity load, it is the gravity load other than the self-weight. So on the first case, we want to find the stress due to the initial full pre-stress and the self-weight itself. And then after that, the question asks the extreme fiber stresses at the midspan, still at the midspan, but at the final service load conditions, wherein the service loads, which are the superimposed dead load and live load, are already being carried by the concrete T-beam, wherein the pre-stress losses have taken place. And then, according to the question, assume that there is 10 diameter 12.7 mm 7-wire strand. So that is the properties or parameters of the pre-stressing reinforcement. It is made up of 10 12.7 mm 12.7 mm diameter 7-wire strand, or 0.5 inches diameter strand. Tendons with a 108-D1 strand pattern, which is used to pre-stress the beam. So that is the parameter with respect to the pre-stressing reinforcement. It is made up of 10 diameter 12.7 mm diameter 7-wire strand. So other parameters given by the question are this. So according to the question, the specified compressive strength of concrete is 41.4 megapascal or 6,000 psi. And it is lightweight according to the question. And then the specified compressive strength of the concrete at the time of initial pre-stress, according to the question, is equal to 33.1 megapascal or 4,800 psi. So what do you mean by this specified compressive strength of concrete at time of initial pre-stress? So if you can remember on our discussion on the previous meetings, we have said that usually the pre-stressing uh, operations or the pre-stress force acting on the pre-stressing reinforcement is usually transferred to the concrete element even before the concrete element attained its specified compressive strength FC prime. So since the concrete doesn't uh, attain since the concrete still doesn't attain the compressive strength of magnitude FC prime at the time when the pre-stressing force is transferred from the pre-stressing reinforcement to the concrete element itself, we have to consider the exact or the specific compressive strength of the concrete at the time when the pre-stressing force is transferred to it. So the compressive strength of the concrete element when the compressive force is transferred to it is what we call the FCI prime, the initial compressive strength of concrete at the time of initial pre-stress or at the time when the pre-stressing force is transferred from the pre-stressing reinforcement to the concrete element. And again, we know for a fact that that magnitude of compressive strength has a lesser value than the specified compressive strength due to the fact that at the time of transfer of the pre-stressing force to the concrete element, the concrete element itself still doesn't attain its full compressive strength FC prime. So that obviously that value will have a lesser value than FC prime. Another given on the question is the FPU, the ultimate strength of the pre-stressing reinforcement, which is equal to 1,862 megapascal or 270,000 psi, which is a stress relief pre-stressing reinforcement. So what we can see here is the specified ultimate tensile strength of the pre-stressing reinforcement, FPU. And then we also have the specified yield strength of the pre-stressing reinforcement, which has a value of 1,517 megapascal or 220,000 psi. So you can see that the FPY and FPU, I mean, if you will compare FPY and FPU, obviously FPY has lesser magnitude because if you can remember on what the stress strain diagram of a pre-stressing reinforcement looks like, if you can remember on our previous discussion, FPY has or I mean FPY occurs long before the pre-stressing reinforcement uh, attained its ultimate capacity or its ultimate tensile strength. So obviously the FPY will have a lower value than the ultimate. So the ultimate is the stress that the pre-stressing reinforcement can withstand. Uh, I mean the FPU is the highest stress that the pre-stressing reinforcement can resist, while the FPY is the stress that the pre-stressing reinforcement uh, experiences before there will be a permanent strain or deformation that will act on the pre-stressing reinforcement. So actually, I suppose you are already familiar with those details because we already discussed those on the stress strain curves or diagrams of pre-stressing reinforcements. And lastly, since it is given that the pre-stressing reinforcements has diameter 12.7 mm 7 wire strand, we can compute for the or actually we don't need to compute for the cross-sectional area of the 7 wire strand, 12.7 mm diameter wire strand, because usually it is already given on the question. And according to the question, it has a cross-sectional area of 99 mm squared or 0.153 inches squared. So we have 10 of those. So if you will multiply uh, 10 by the 99 mm squared, which is the cross-sectional area of the pre-stressing reinforcement, you can find the total area of the pre-stressing reinforcement. So that is the area of the pre-stress longitudinal tension reinforcement. Although if you will try to compute the area of a 7 wire strand which has a diameter of 12.7 mm, using the formula for a circle, which is pi over 4 d squared, diameter squared, you can notice that this value you see here is somehow different from that value that you can that you will compute using the diameter 12.7 mm. So the reason for that is actually the 12.7 mm that is given here is just the nominal diameter. So it is not actually the total cross-sectional area. So if you can remember the what is the cross section of the of a 7 wire strand looks like, if you can remember on our previous meeting, it is not a circular cross section. Actually, it is composed of 7 wires. So the wires has its own cross sectional area, and they are just being twisted together to form a 7 wire strand. So you can see that it is not actually a circular cross-section, but a cross-section composed of several wires or circular sections. So the nominal diameter of that uh, 7-wire strand is 12.7 mm. So you can, if you will try to compute, it will have a different magnitude of area compared to the given here. So this is the cross-sectional dimensions of the given T-beam. So this is the T-beam. According to the question, its cross-sectional area of the concrete T-beam is equal to 2897 centimeters squared or 449 inches squared. And then it has a neutral axis somewhere here, which is obvious. If you will try to compute the location of the neutral axis, it will obviously be located somewhere here due to the distribution of the area on the cross-section. And then given on the problem is the moment of inertia of the concrete with respect to that neutral axis, because the beam tends to bend with respect to that neutral axis. So the given moment of inertia uh, must be in reference to that particular neutral axis, and it has a magnitude of 935 230 centimeter to the fourth, or 22,469 inches to the fourth, according to the problem. And then the C with respect to the bottom fiber is equal to 451 mm or 17.77 inches. So the distance from the neutral axis to the extreme bottom fiber at midspan, according to the problem, is 451 mm or 17.77 inches. And with respect to the top fiber, the distance from the neutral axis to the top fiber, according to the problem, is 158 mm or 6.23 inches. And with that, using those CB and the given moment of inertia, we can compute for the section modulus at the bottom, 20,7137 centimeter cube or 1264 inches cube. Although actually these things are already given. These are actually the properties of a 10 LDT 24 double T beam. So it is actually given on the question. So as well as the section modulus with respect to the top fiber, 59,108 centimeter cube or 3,607 inches cube. So the particular dimension of the T-beam is this. So the total width is equal to 10 feet. The thickness of the flange, this is actually what we call flange of the T-beam. The thickness of the flange is equal to 2 inches. And then the distance of the webs of the T-beam is equal to 5 feet. The width of the web, the bottom width of the web is equal to 3 3/4 inch or inches. Then the total height of the T-beam itself is equal to 24 inches. And the upper width of the web is equal to 5 3/4 inches. Actually, these dimensions are not irrelevant anymore because the cross-sectional properties are already given. But in the case of the cross-sectional properties are not given, you have to compute all of this using the given dimensions. And then the T-beam will support superimposed dead load due to topping, which has a thickness of 2 inches. So actually, that is where the superimposed gravity dead load of WSDL came from the topping. And the live load came from obviously the occupants that is intended uh, to be supported by this concrete element. So those are the given on the problems. So you can see on the subject pre-stress concrete design, uh, every problem usually has many given, especially the dimensions and the cross-sectional properties of the cross-sectional area. So you can expect from now on, you can expect that we will have a very long question and very uh, many details about the question. So, because that is how pre-stress concrete design works. You need many information for you to be able to analyze and design pre-stress concrete members. So without further ado, let us now address the first goal, which is to compute the extreme fiber stresses at the midspan. So we know for a fact, if you can recall, if you will just try to recall, how can we compute the stresses acting on a concrete element, especially a simply supported beam? If you can recall on our discussion, the the total stress acting at the pre-compressed zone, which is the zone which is originally experiencing compressive stresses as the concrete element supports its own weight, which is in this case the upper portion of the concrete above the neutral axis, although or in general the upper portion of the concrete element. So that is the pre-compressed zone. So if you want to find the stresses there, you can use this formula. You can just change the value of C depending on the particular location of the fiber you are investigating. So if you will want the extreme fiber stress, you can use this, the extreme distance from the neutral axis, those C. And in the case of the stress at the pretension zone, which is the lower portion of the concrete element on this case, because if you can imagine, if the concrete element will support its own weight, the tendency is it will experience tensile stresses at the lower portion. So that is the what we call pretension zone. And if you want to find the stresses acting on that pretension zone, you can use this formula. You can just change the value of C depending on the location of the fiber you are investigating. But if you want to investigate the extreme fiber, which is located on the bottom, you can just use the distance CT, which is the distance from the neutral axis to that extreme bottom fiber. So according to this formula, we can compute for the stresses at midspan if we know P and M, because the other parameters you can see here are already given on the question, especially the E at midspan, which is equal to 375 mm. So the only unknown parameter here, in order for us to compute the stresses at the extreme fiber of the concrete element, are the P and the M, which are in the case, if you can remember, P and M at the initial pre-stressing stage at transfer, P and M uh, has a value of Pi for the case of P and 0 for the case of M for initial pre-stressing at transfer. So Pi again, may I just recall that Pi is the initial pre-stressing force before losses. So that is actually the initial pre-stress force that is being transferred to the concrete element as you cut the pre-stressing reinforcement. And then at that particular stage of pre-stressing, there is still no moment being induced on the concrete element because the concrete element itself is still fully supported by the precasting bed. So the moment acting on the concrete element is zero, equal to zero, because there is no moment from transverse loads, especially the self-weight, at this particular stage of pre-stressing. And then after that, because of the eccentricity of the pre-stressing force, the beam tends to bend upward, thereby producing a camber. And when the concrete is already on that stage, we can say that the concrete is already on this stage, which is the initial pre-stressing at transfer with self-weight, because the camber or the scenario where the concrete element bends upward forces the concrete element itself to support its own weight. Thereby, it will already produce a moment inside the concrete element due to that dead load or the self-weight of the concrete element itself. But still, the pre-stressing force is still the initial pre-stressing force PI before losses, before the before the different pre-stress loss occur on the pre-stressing reinforcement. So at this particular question, the case that the question asks is this stage of pre-stressing, wherein the magnitude of P on this formula is equal to the PI, the initial pre-stressing, and the magnitude of M is equal to the moment due to the dead load. So if we can compute for the magnitude of PI and MDL, therefore we can already solve for the stresses acting on the concrete element itself. So now let's try to compute for the magnitude of PI. So how can we compute for the magnitude of PI, the initial pre-stressing force acting on the pre-stressing reinforcement? So if you will go back to the question itself, it is stated there that the initial pre-stress before losses is equal to the 70% of the ultimate strength of the pre-stressing reinforcement. And if you can recall on mechanics of deformable bodies, the relationship between the stress, force, and the cross-sectional area, according to mechanics of deformable bodies, uh, the force is equal to the stress times the cross-sectional area. Or since we are talking about the initial pre-stressing force here, we can say that the initial pre-stressing force is equal to the initial pre-stress, which is given here, 70% of the ultimate tensile strength of the pre-stressing reinforcement, times obviously the cross-sectional area of the pre-stressing reinforcement itself. So the FPI, according to the problem, is 70% of FPU. And if you can recall, the FPU is given on the problem as well as APS. So APS is 10 diameter 12.7 mm, and the cross-sectional area of that 7-wire strand, according to the problem given before, is equal to 99 mm squared. So we can just substitute all of those values here. So if we will substitute them, FPI is equal to zero point 0.7 FPU. Zero point 0.7, this is the magnitude of FPU, and the magnitude of the total cross-sectional area of the pre-stressing reinforcements is equal to 1099 mm squared. So this is the product of this is actually the initial pre-stressing force. Although if you can notice here, the product will be in terms of Newton because this is in terms of megapascal or Newton per mm squared, and this is in terms of mm squared. So the product is supposedly in terms of Newton, but I prefer to express it in terms of kilonewton. Although I did not put anymore the conversion factor, which is the which is the divisor of 1000, because we know that 1 kilonewton is equal to 1000 newton. So I just did not put anymore the conversion factor, but I suppose you can uh, already understand how this value was computed. So you just have to divide this product by 1000 to make it in terms of kilonewton. So that is the magnitude of PI. So the only thing left to be compute or to compute is MDL, which is the moment due to the dead load or the self-weight itself. And we know for a fact that the moment acting at midspan of a simply supported beam is just equal to WL squared over 8, wherein W is the uniformly distributed load and L is the total length of the simply supported beam, which is equal to 19.51 meter. So if we will just substitute all of the values, we can compute for the moment due to dead load, wherein W, the dead load or the self-weight of the member, is equal to 5.24 as given by the problem, and the length of the member is 19.51 meters, which is also given on the problem. So if you will compute that value, you can compute for this moment due to the dead load. So obviously it has a unit of kilonewton meter. If you will try to check the resulting units depending on the given on the formula. So there, we already computed the magnitude of PI and MDL. Therefore, we can now compute for the stresses acting on the concrete element itself, on the extreme fiber reinforcement, extreme fiber at the top and extreme fiber at the bottom fiber. So you will just have to substitute all of those values on this formula. So if we will try to substitute, we will have this expression. So for consistency of units, I just chose to express all the forces in terms of Newton, and then all of the area in terms of mm squared, moment of inertia in terms of mm to the fourth, and the C and E in terms of mm. And then M will be expressed in terms of Newton mm's, so that the, the units will be consistent and the resulting unit will be equal to megapascal or Newton per mm squared. So we will just have to substitute the value of P, which is equal to Pi, and then we just have to express it in terms of Newton, and then AC, moment of inertia, and the E, eccentricity at midspan, is equal to 375, and then C, the distance from the neutral axis to the extreme pre-compressed fiber, which is equal to 158 given on the problem. So we can compute for the extreme fiber stress at the pre-compressed zone, as well as the extreme fiber stress at the pre-tension zone. So actually we can just copy this and then change the sign of this two, and change the magnitude of the C, because we all know that the C with respect to the bottom fiber is different from the C with respect to the top fiber. So we will use the C, or the distance from the neutral axis to the bottom fiber, equal to 451, which is given on the problem. So if you will compute these two equations, you will see that the stresses acting on the extreme pre-compressed fiber is equal to this, and on the extreme pre-tensioned fiber is equal to this. So both are compressive stress according to what we have computed. Since we have computed that the stress is equal to negative, and we know for a fact that our sign convention wherein we designated negative stresses as compressive forces and the tensile stresses as positive. So since the values we have computed are equal to negative value, therefore the stresses acting on the concrete element at the extreme fibers are all compressive stresses. But before we accept that, or before we accept those answers, we have to check first if these stresses acting on the concrete element itself are compliant to the code provisions. So in order for us to check if they are compliant to the code provisions, let us just check the the provisions itself. So if we will check the provisions of ACI 318M-14 on the section 24.5.3, the permissible concrete stresses at transfer of pre-stress. So take note, the stresses that we are computing here are the stresses acting at the concrete element at transfer. So we will use this particular provision of the code because it states the permissible concrete stress at transfer, specifically the limit on the compressive stress at transfer, which is given on this table. Or if you will want to refer on our local code NSCP C101-15, you can see similar table. So according to this table, at transfer stage, the maximum permissible stress that must act on the concrete element itself with respect to the compressive stress must not exceed the values given here. So we have two formulas given here. So the first one is the limit on the compressive stress on the ends of simply supported members, and the other one is the limit on the compressive stress on all other locations. So the question at hand falls on the second row of the table because we are concerned on the stresses at midspan and not on the ends of a simply supported member, which is what is described here on the first row. So we will use this second formula, the all other locations. So these compressive stresses at transfer must be less than 0.6 of FCI prime, the initial compressive strength, which is given on the problem, which is equal to 33.1. So we will just compute for the 60% of that initial compressive stress, which is equal to 19.86, and these stresses must be less than or equal to that limiting compressive stress at transfer if we want to say that these stresses are code compliant. So obviously, if you will compare this stress to this stress, obviously it is less than the maximum permissible compressive stress at transfer specified by the code. So therefore, the stress at the extreme fiber pre-compress, uh, I mean the stress on the pre-compress extreme fiber is okay. So we will just put an okay there. So therefore, since it is okay, it is code compliant, we can now take it as the final answer for letter A for the first question. And then for the uh, pretension extreme fiber stress, if we will compare it to the limiting value specified by the code, which is again still this value because it is still a compressive stress, we can see that it is still less than the maximum permissible stress specified by the code. Therefore, it is okay. So therefore, we can take it as the other final answer. So these are the stresses acting on the extreme fiber of the concrete element at midspan at transfer stage. So you have to take note which particular stage of pre-stressing are you computing the particular stresses, because that is important. That is actually the basis of the particular code provision that you will use in terms of the maximum permissible stress. And if you will take note, you can just disregard the negative sign here if you are comparing the magnitude of the stress that you have computed to the maximum permissible stress specified by the code, since we all know that the sign just indicates if whether if it is compressive or tensile stress. So again, the negative sign there just indicates that the stress is actually a compressive stress. But if you will compare it to the actual magnitude of the maximum permissible stress specified by the code, you can just use the magnitude only. You don't need to include the sign, because again the sign just indicates whether it is compressive stress or tensile stress. So the other question is, the question wants to find the extreme fiber stress at the midspan, still at the midspan, but on the final service load condition, wherein the superimposed dead load and live load are already being carried by the concrete element itself. So before, on the previous situation, the the transverse load being supported by the concrete element is just its own weight. But now, on the second situation given on the problem, the service loads, which are the additional service loads, which are the superimposed dead load and live loads, are already being carried by the concrete element itself. So the problem or the question wants us to find extreme fiber stresses at midspan, still at midspan, on that particular stage of distressing. So if you can recall the service load condition, on the stage of service load condition, which is the uh, another stage of pre-stressing. If you can recall, on the service load condition, the P, the pre-stressing force acting on the pre-stressing reinforcement, is already the effective pre-stressing. So we know for a fact that the effective pre-stressing or the effective pre-stress force has a lesser magnitude than the initial pre-stress force, due to the fact that the initial pre-stress force uh, actually diminishes in value due to pre-stress losses, which have several reasons why those pre-stress losses occur. So we will discuss those reasons, those causes, later on the next chapter. So when the initial pre-stress force experience losses, it uh, it reduces its magnitude down to a magnitude of PE, which is again the effective pre-stress force. So this is the effect. This is the pre-stressing force uh, acting on the pre-stressing reinforcement after those losses already occurred on the pre-stressing reinforcement, which tended to or which are the reason why the initial pre-stressing force diminish in value down to a value of PE, the effective pre-stressing force. So that is the magnitude of the pre-stressing force acting on the pre-stressing reinforcement at service load. And then the moment being experienced by the concrete at the service load condition will now be the moment due to the dead load or the self-weight itself. And then additional to that, because there is an additional load, which are the superimposed dead load and live load, there will be additional moment that will be induced on the concrete element itself, which are the moment due to the superimposed dead load and the moment due to the live load, superimposed live load. So we can still use these formulas, but we can just replace the magnitude of P and M by these values. So if we can compute for these values, the PE and the total moment we see here, we can now compute for the total stress acting on the extreme fibers of the concrete element itself. So now, without further ado, let's compute first for the magnitude of PE. So same way, same method on how we computed the initial pre-stress force, the PI. We will just recall again the relationship between stress, the force, and the cross-sectional area. So again, uh, according to mechanics of deformable bodies, stress is just equal to force over area, or if we will try to make it in terms of the force is equal to stress times the cross-sectional area. But since we are considering the effective pre-stressing force, PE, therefore the stress must be also the effective pre-stress, which is given on the problem equal to 1034 megapascal or 150,000 psi, and the total cross-sectional area of the pre-stressing reinforcement, which is 1099 mm squared, 7-wire strand. So we just have to substitute all of those on this formula. So the FPE is equal to 1034 given on the problem. Cross-sectional area total of the pre-stressing reinforcement, 1099 mm squared. So again, the product will be in terms of Newton because this is Newton. This is in terms of Newton per mm squared or megapascal, and this is in terms of mm squared. So the product will be in terms of Newton, but I just uh, chosen or I just chose to express it in terms of kilonewton. So I just divide it with 1,000 because again, we all know that 1 kilonewton is equal to 1,000 Newton. So I suppose there will be no problem on conversion here. So that is the effective force acting on the pre-stressing reinforcement at service load when the concrete itself already carries the additional load due to the superimposed dead load and live load, which has a sum of 6.13 according to the problem. So the next thing that we have to compute is the total moment. And again, we know for a fact that the moment at midspan in a simply supported beam is equal to WL squared over 8, wherein our W will now be the total of the dead load itself or the self-weight itself and the additional load which came from the superimposed dead load and live load, which have a sum of 6.13. So we just have to add the sum of the superimposed dead load and live load to the weight of the dead load itself. So that will be our W. L will be still the same, 19.51 meters over 8. So the moment due to the all of the service loads is now equal to 540.98 kilonewton meter. So since we already computed for the value of P and M, all we have to do is substitute them on these formulas. So substituting those values to the corresponding formula here, if we want to find the extreme fiber stress at the extreme pre-compressed fiber, we can just use this. So we just have to replace P by the PE that we have computed a while ago. But again, for consistency of units, let us just express all forces in terms of Newton, area in terms of mm squared, distances E and C in terms of mm, and moment of inertia in terms of mm to the fourth. So let us just change this into Newton. So we just have to multiply it by 1,000. So this is the cross-sectional area given in the problem. Eccentricity at midspan given at the problem, 375. The distance from the neutral axis to the extreme top fiber equal to 158. given on the problem again. Moment of inertia given on the problem. C, just copy here. I, just copy here. Moment due to the total load. You can use this, but you just have to express it in terms of Newton mm. So you just have to multiply the magnitude of 540.98 by 10 to the 6, because the conversion factor from kilonewton meter to Newton mm uh, is you have to convert kilonewton to Newton, so you have to multiply it by 1000 to make it Newton, as well as as well as meter, you have to multiply it by 1000 as well to convert it to mm. So for the stress at the extreme pretension fiber, you can just copy this equation here, and you can just replace this sign by the negative sign as well as this sign. You just have to change those signs as well as the magnitude of C, because we have now a different distance from the neutral axis to the bottom fiber, and according to the question, that distance is equal to 451. So you can just copy that uh, equation there if you want to simplify the computation, and then change the sign here, and as well as the C. So if you will compute the value, if you will try to compute this on your calculator, you can see, you can have this value, and if you will compute this expression here, you can compute for this value. So you can see that the stress at the extreme pre-compressed zone is actually a compressive force, while the stress at the pretension extreme pretension zone is equal to 4.043 megapascal, which is a tensile stress because it has a positive sign. So before we accept this as the final answers, we have to check first if these stresses comply with the code requirement, with the code limitation in terms of the permissible stresses that can be permitted to be experienced by the concrete at service load condition. So we have to refer to the particular provision of the code that pertains to the maximum permissible stresses at service loads. So let's go first on the maximum permissible stress at service load in terms of the compressive stress. So you can see here on section 24.5.4.1, you can see a table there, as well as if you will use the local code, you can see a similar table. So you can see that the table has two rows. So it has two magnitude of permissible stresses, compressive stresses to be particular, that can be experienced by the concrete at service loads. So for the first row, it states that you can use this limit, compressive stress limit, if the load condition is pre-stress plus sustained load, while you can use this other formula if the load condition is pre-stress plus total load. So which of these will we use? So we will not use the second row formulas because that pertains to the uh, total load condition, wherein the concrete element already supports all of the loads that are intended to be supported by it. In this case, we're just considering the service loads, or the dead load, superimposed dead load, and the live load. So it is just the sustained load, not the total load, because the total load is composed of the wind load, the earthquake load, and other loads that the concrete element are supposed to carry later on its life. So we will just use the pre-stress plus sustained load. So according to this table, according to this particular provision of the code, uh, the maximum permissible compressive stress at service loads that can be experienced by the concrete must not exceed 45% of FC prime. So what is 45% of FC prime? Our FC prime is equal to 41.4. It is given on the problem. And its 45% is equal to 18.63, which is obviously greater than the stress that we have computed on the pre-compressed extreme fiber. So therefore, since that magnitude is equal to the maximum permissible compressive stress stated on section 24.5.4.1, or if you will refer on NSCP on section 424.5.4.1. Therefore, the stress that we've computed here is okay. So therefore, we can accept it as the final answer. But we still have to check the other stress that we have computed, which is a tensile force. So what particular code provision will we use to check if it is code compliant? So actually, you can refer on the section 24.5.2.1, or if you will refer to NSCP, the local code, you can refer on section 424.5.2.1. You can refer on the table given, so the two codes has or have similar table, because again, we know for a fact that our local code adopted this international code, the ICI code. So if you will look on the table, you can see here the stress limitations for you to be able to say that the section of a concrete is still uncracked or cracked. So again, if you can remember on our very first discussion, we are saying that we want our pre-stressed concrete element to be uncracked, meaning we don't want it to be on the to experience cracking. And according to this table, uh, if the concrete element will now have well or if the concrete element will experience a tensile strength greater than square root of fc prime, you can say that the concrete element itself is already cracked according to this table. So now, at service loads, actually these are at service loads. So now, if we will try to think what will be the limiting tensile stress for us to be able to say that our concrete is still code compliant, which is uh, which is the code states that we have to maintain the concrete from being uncracked. So therefore, we must not let it to crack, or in other words, we must not let it experience a tensile stress equal to square root of fc prime. So therefore, that will be our limiting value for the maximum tensile stress that the concrete element can experience at service loads. At service loads. So therefore, this uh, tensile stress we have computed here must not be greater than square root of fc prime, because we know for a fact according to this code that if the tensile stress acting on the concrete element at service loads will be greater than square root of fc prime, therefore we can already consider it as crack, which is the scenario that we are avoiding. So in order for us to not say that the concrete is already cracked, we must make sure that the tensile stress being experienced by the concrete element must not be greater than square root of fc prime. So therefore, our maximum permissible tensile stress here at service loads must be square root of fc prime, which is equal to 6.43. Our fc prime is 41.4 given on the problem. So by comparing the two, we can see that the maximum stress given on the code is obviously greater than the tensile stress that we have computed here at service loads. Therefore, we can say that that tensile stress is okay. It is called code compliant. It doesn't exceed the maximum stress specified by the code, wherein you can say that the concrete element is already cracked. Therefore, we can take that stress as the final answer here, the other final answer. So these are the stresses being experienced by the concrete element at service loads. The two values we have computed a while ago are the extreme fiber stresses that the concrete element experiences at transfer. So you have to take note in this type of problems, guys. You have to take note what is the particular stage of pre-stressing that you are uh, considering, because that stage will be the basis of what particular provision of the code you will use on checking the stress limitations, the maximum permissible stresses. So there, we already understand the basic concept method of designing pre-stressed concrete elements, and we also applied it in designing or analyzing a pre-stressed concrete element. Therefore, we already addressed our first goal. So now, to address our second goal, which is to understand the C-line method of designing pre-stressed concrete elements, we will now be discussing the theoretical background of this second method of designing pre-stressed concrete elements. So without further ado, let us now discuss the C-line method.